Hello everyone, welcome to topic 3.4, Ideal Gas Law. For this, you should be able to explain the relationship between the macroscopic properties of a sample of gas or mixture using the ideal gas law. Now, I do understand that we did not cover this in your first year of chemistry, but we are going to cover it here. So, we will do a lot more practice with this, but we're going to get started with these. Okay, and so there are some equations here. There are more equations over here that gave rise to the ideal gas law. So we have building block gas laws that describe how properties of a gas respond under certain changing conditions. We have Boyle's, Charles, and Avogadro's. There is Gay-Lussac and a few other people who gave different gas law equations. We'll get to them in future sections as well. But here are some that help us start. These all gave rise to the ideal gas law. We have the relationship here and the formula. Using these, somebody smart put together the ideal gas law, which is PV equals nRT. And this is used to relate the pressure, volume, moles, and temperature of a sample of gas by using the gas constant R at a given state of conditions. So we have all of these PV equals nRT. This might actually be something really important to put on your one-pager. There are several R values listed on the equation sheet. They differ in the units for pressure. So on the equation sheet you have that equation above, and you also have multiple gas constants besides just the 0.08206. You have the 62.36 and the 8.314. Make sure you always check your units that you're given, and it's usually going to be pressure is going to be the one that you need to check. So for whatever pressure unit you have, you need to make sure you're using the gas law that has the matching pressure units. Okay. The ideal gas formula can be used to solve for the molar mass or density of a gas, and we have that here. And then we also have a related law, that is Dalton's law of partial pressures, which states that the sum of all the partial pressures of each gas in a mixture of gases is equal to, somebody can't spell, the total pressure. Okay. In mathematical notation, this is expressed by saying P total is equal to PA plus PB plus BC plus so on, where A, B, C, and so on are different gases. So we have this illustration here. This is often used when gases are collected over water, as shown in the image that is below right here. Okay. As the gas is produced, the water is displaced and in the inverted vessel and will empty while the gas is collected, and the gas is collected in the area above up here. This method allows for the gas to be measured and minimizes the amount of room air that could contaminate the sample, because some of those will react with whatever gas is collected in there. However, as the gas travels through the water, it will pick up water vapor, which will contribute to the gas being produced. The amount of water vapor that is picked up is a function of the temperature of the gas and can be subtracted using Dalton's law of partial pressures. And please remember that part, subtracted using Dalton's law of pressures, because that is in either the I do, we do, or it's in your you do's. When the water is subtracted from the gas, it is described as dry because it no longer has water in there. And this table tells you what the water vapor pressure is at various temperatures Celsius. Additionally, we can use mole fractions, which is denoted by chi with the substance A in this part, and it's equal to the moles of A, or that gas, divided by total moles. So what fraction in your gas sample is one or the other? So if a mixture is 3 moles of O2 and 4 moles of H2, The mole fraction of oxygen gas is 3 from the oxygen divided by the total number of moles, and in this case it's 0.43 for the mole fraction. To find partial pressures, you multiply the mole fraction by the total pressure, and so they have that here. Okay, so this one is a little bit math heavy of a section. So for the I do, and remember for these you're going to either use stoichiometry or the equations given to you in all of these I do, we do's, you do's. So for the I do, when heated strongly, solid calcium carbonate decomposes to produce solid calcium oxide and carbon dioxide gas as represented by the equation above. A sample of calcium carbonate is placed in a rigid 35-liter reaction vessel from which all the air has been evacuated. The vessel is heated to 437 degrees Celsius, at which time the pressure of the carbon dioxide in the vessel is constant at 1 atmosphere. Calculate the number of grams of calcium carbonate that reacted to produce the carbon dioxide gas. Okay, well, grams is what we want to know, right? So we got to be able to get some sort of amount. Well, when we look, we are given a volume and a pressure and a temperature. Well, pressure, volume, temperature tells me ideal gas law, PV equals nRT. And this is one of the equations introduced at the beginning of these notes. Okay, this is also given to you in your equation sheet that is on the AP test. So if I know this is all for O2 because it's the only gas, or not O2, CO2, because it's the only gas in the system. The other twos are solid. So we can solve for N using the pressure of carbon dioxide, the temperature, and the volume. But this N would be of CO2. So, and this N is moles, so this would give me moles of CO2. So from there, I can take the moles I get of CO2 and I can convert that to moles of calcium carbonate and then to grams of calcium carbonate using stoichiometry. So we're going to do that. So we'll substitute in all the variables we know. So pressure was given to us as 1 atmosphere, or ATM. The volume was given as 35 liters. N is what we're going to solve for, so we can even call that X. I'm going to leave it as N. And then the gas law constant that we're going to use, we need to match our units from the first page of the 3-4 notes. And that would be 0.08206, and this is on the equation sheet as well. So ATM, liters over mole Kelvin. I know that this is the correct one to use because the atmosphere units. That matches my units for pressure. So the units in my gas law constant R should match the units I am using or need to use in my ideal gas law equation. So then here, when I do temperature, I notice that the temperature is in Kelvin. We'll define degrees Kelvin. I take K and I take my degrees Celsius, 437, take degrees C and I add 273. Oh, look at that, it rhymes. And you should get 710 Kelvin. So that is what I would use in my ideal gas law, because now the units match. You will not use degrees Celsius in here because Celsius can be negative, but the temperature is never negative in the ideal gas law equation or in any gas law equation. So using this and solving for N, you should end up with 0.601 moles of carbon dioxide, because that is the only gas in ideal gas law is for carbon dioxide. It's for gases, so carbon dioxide. So I did my first step. Now I can do stoichiometry to find the mass of calcium carbonate. So starting with the moles of carbon dioxide, forgot my unit. I can convert it, and so I said first I need to go to moles of calcium carbonate, And then I can go to grams of calcium carbonate. And I drag units diagonal so that they cancel as I go towards my goal. So moles to moles is my mole ratio, which is from the reaction, and I check and it is balanced, so I say 1-to-1 ratio there. And then the molar mass is grams per mole, and that's 100.09 grams, because I add up all the periodic table masses for 1 mole. So when I solve this, my units cancel, and I'm left with just grams of calcium carbonate, which is what I was asked for. And then I'm going to multiply across the top and divide by the bottom. So 0.601 times 1, that's boring, divided by 1, that's boring too, times 100.09, and then divided by 1 again, is 60.2 grams of calcium carbonate. And that is my answer. If we move to our we do, we're going to use the ideal gas law again here. So a basketball is left outside in winter when the temperature is -2 degrees Celsius. And it has a volume of 6.88 liters, and the pressure inside the basketball is 0.795 atmosphere. Okay, so I am given a temperature, a pressure, and a volume. It wants to know how many moles of gas are in the basketball. So that's my first question. And then my second question is, what is the partial pressure of oxygen in the basketball? So for the first question, how many moles of gas? Well, I'm given temperature, pressure, and volume, and I want to know moles. Well, that tells me pressure, PV equals nRT. Use my ideal gas law equation. So pause the video and solve this part. Resume the video when you're ready to check your answer. Okay, so you should have solved for N by substituting in pressure, volume, and then your temperature should be degree C, so -2 plus 273 to get Kelvin, which would give you 271 Kelvin, and that's what you would use in here. And then you match your units for your gas constant. Using algebra to solve for N, you end up with 0.246. Now this is your moles, total moles of gas. For number 2, it says, what is the partial pressure of oxygen in the basketball? When I know what the total pressure is, right, it is here given to me as 0.795. We'll define the pressure of one of the gases, that's the partial pressure of oxygen. I'm going to take its mole fraction, what fraction it is of anything in this sample. So I'm going to take that 0.209, kind of think of that as like its percent, but you're counting particles, so it's not by mass. And you're going to multiply it by the total pressure. So this is part of Dalton's laws of partial pressure, and the units are ATM. So the part out of the whole times the whole of the gas pressure, and when you solve that, you should end up with 0.166 atmospheres of oxygen gas. So that is the partial pressure of oxygen. If you wanted to find the partial pressure of nitrogen or of argon, you would do the same thing. You would just use their own mole fractions. Okay? So this concludes this section of notes. Now, I can't show you every single way that we can do math with the gas laws. So you need to try, and then please check your answers. All of the equations you need are given in the notes. Think about what it's asking you for. Find that equation in your notes and utilize it as you work through the you-dos. Check your work either as you go or when you are done. Thank you, everyone.